All right. So yesterday we left off talking about spanning trees. Okay, we left off talking about spanning trees. Where did I just put my remote? I need a nap. Oh my. It's almost as bad as I was on the phone with my dad one day and I'm like, oh, my dad's like, what's wrong? I was like, I can't find my phone. He goes, honey, you're talking to me on it.
Oh my god, that's
sad.
Oh, I totally got mad.
I know. Oh my god. I be like, where's my toothbrush? Where's my toothbrush?
I just said to them, I said, where's the remote? And they're like, in your hand.
I do that with my glasses.
How do you know?
All right, back up here. So, number 1A, is this graph a spanning tree?
No.
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 Why?
It's that circuit.
There's several circuits here. Okay, you've got a huge circuit, you've got a little circuit, you've got this little circuit, you've got this little circuit. Okay, there's a crazy amount of circuits in this graph. So this is automatically a no. So I want to draw a spanning tree from this graph. How many edges do I need to use to create a spanning tree?
1, 2, 3,
6.
4.
How do you know that, Thomas?
There's 6 dots. No, there's 7 dots.
There's 7 dots. So my vertices are 7, which means to have a spanning tree, I need 6 edges. Okay? So if this is A, B, C, D, E, F, and G, what edges do you want to use to create a spanning tree?
A to B, B to C,
G to C.
G to C.
All right, hold on. A to B,
B to C, C to G, and then A to E,
A to E,
E to F.
E to F, and then B to D.
D to D. Okay, that works.
Or you could do C to D. And then
Okay,
A to
you
D.
could do C to D, you could do A to D. So every dot is connected, and we've used 1, 2, 3, 4, 5, 6 edges.
I like it.
Oh my gosh.
I like this tree thing. I really admire what it does. It fluctuates my brain cells.
Fluctuates your brain cells. Oh my. Listen, I'm telling you right now, if he does not make me go famous on YouTube, I don't know what will, because, you know, people are probably watching this video laughing hysterically over his stupid comments.
I would. Yes.
I
know this. I would watch.
Right. They're gonna be like, I gotta tune in tomorrow. See what Rodrigo says.
I would.
Right. Will he like it? Will he not?
I like A or number 2A because it's already a tree. So you don't have to do anything, brother.
Okay. Rodrigo says he likes 2A because it's already a tree. So do I need to find a spanning tree?
No.
But you can still do it.
No. I said no.
Be the same exact graph.
I do not like that.
You just have to.
But you're right.
Who said that? Who said that?
I'm gonna start my own little like sitcom. Does Rodrigo like it or not? Kind of like, you know, the radio station that does like Dale Knows Everything. I'm gonna call it Rodrigo Likes It.
Just like tell him stories over video. Just comments that he likes.
Right. All right. So
People are gonna be mad.
leads me to the fourth property of Dan hitting the floor. You all right there, friend? Okay.
I didn't like that. Are you okay?
He didn't like that.
I think it's.
Rodrigo didn't like that.
Are you right?
All right. Okay. So, property number 4 says, if a network, again, that means if I have a connected graph that has B vertices and E edges, if my edges are greater than or equal to my vertices minus 1. What in the world does this mean? Holy crap. Okay, so we have something called redundancy. Okay, so the redundancy is the difference of your edges and vertices plus 1. So they're saying that you can find what we call redundancy by taking your edges, subtracting your vertices, and adding 1. And that will give you R. Okay. I don't like to use the formula. I think it's confusing. So I'm going to show you how I do it, show you how you get it the same way with the formula. You figure out which way works better for you. Okay, so let's go back to this. So in my original graph, we have 7 vertices. Okay, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. What should my edges equal if this was a tree? 6. This should equal 6. So what do I need to get rid of to get 6? If I started with 9 and I needed to go to 6, we get rid of 3. That's your redundancy. So your redundancy tells you how many lines you need to get rid of to create a tree. So if I would have used the formula says 9 minus 7 plus 1. Well, 9 minus 7 is 2, plus 1 is 3. They both do the same thing.
I like both of them, so it's okay.
So, again, I don't ever remember the formula, so I don't use it. I just know that my edges should always be 1 less. So what do I have to do to my number to get down to that number? Okay. So let's go back to this one.
Oh.
Okay, so this one had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 edges. So I need 1 less edge to make it 12. So my redundancy is 1. I need to remove one of my edges for this to become a tree.
Why would they throw it? It's so confusing when something should be so simple.
Okay. This one, I've got 1, 2, 3, 4, 5, 6, 7, 8. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. I need 10 to become 7. So I need to remove 3. So my redundancy is 3.
Oh.
Okay. Does that make sense?
Yes.
Okay. Like I said, I don't ever remember the formula. It's not something that sticks in my head. So, but if you can do the formula, so E, take away V, plus 1. 10 minus 8 is 2, plus 1 is 3. It still works. So it's entirely up to you. You're gonna have to find redundancy on your test.
Wakey, wakey.
Hey, friend. He's like,
That's how it be.
And you gotta work.
Andy's got a game tonight. Woo! Okay, so if you use this formula and your redundancy comes out to be 0, that means we have a tree. If your redundancy is 0, you have a tree. So if you think about it, if my vertices are 7 and my edges are 6, that would mean 6 minus 7 plus 1. Well, 6 minus 7 is -1, plus 1 is 0.
So if your redundancy is on more or less,
It would never be less because it would automatically be disconnected and you wouldn't even have to do redundancy.
So
Okay.
you
So-
would end up as more.
Yes. If your redundancy comes out to be a number that's greater than 1, it's automatically not a tree. It's automatically not a tree. Questions? Less than 1?
You can't add anything to it.
So Thomas asked, why can't this be less than 0? So here's why. If I have 4 vertices and I draw this, why is this automatically not a tree?
Not connected.
It's not connected. So this would be an instance where your R would be less than 0 because my edges are 2 minus 4 plus 1 gives you -1. It's never going to happen because you automatically know that this is not a tree because it's disconnected. So the only time that you would ever end up with a redundancy that's negative is if you already had a disconnected graph, which you wouldn't even need to calculate redundancy because you already know. Does that make sense? Okay, that's a good question. I love this as I teach it longer because some of y'all come up with really good things that other people never even thought about. Or they don't ask. Okay. So this is the next concept. How do I find how many spanning trees are in my graph? So the first thing we need to figure out is how many edges do I need to remove? Okay, so we need to figure out the redundancy. So how many vertices do I have in my graph? 8. How many edges are in my graph? 8. So I need that to become 7, so I need to lose 1. So I need to remove 1 edge. What edge do I need to remove? H to C. Is that my only option?
No, you can do H to D.
I could remove H to D. What?
No, you can't do that one.
Not D to G, because that would disconnect my graph. You don't want to get rid of any bridges. There is one more.
C to D?
C to D.
Oh, yeah.
Okay. So I could remove H to C. And if I do that, my graph's going to look like, let's see if I can do this. 1, 2, 3, 4, 5. If I remove H to C, my graph looks like this. Well, that's a tree. If I remove H to D, that means H to C is back in. That's also a tree. If I remove C to D, H to D goes back into play. This is also a tree. So there are 3 different ways to create a spanning tree. How do we know that though? There's 3 spanning trees. What do these 3 edges do?
They all connect.
They're all connected, so they are a circuit. Okay. All 3 of these edges created the circuit that I needed to break up. So I need to break up that circuit, and there's 3 ways to break up that circuit. So there are 3 spanning trees available. So any graph that has 1 circuit in it, however many edges are in that circuit, means that's how many spanning trees you have. Okay? These are the easy ones.
Is there ever a case where just as many?
Here's this one.
C, H, D.
Jesus Christ.
It's just his accent when he says that. It just cracks me up every time. Oliver's. All right. So again, let's figure out how many edges I need to remove. So I have 8 vertices, and I have 9 edges this time. I need this to drop to 7. So how much do I have to remove? 2. So we need to remove 2 edges.
C.
All right. So this is the one that we dealt with last time, was this one. We said I could remove any one of these 3. But this time, instead of just having 1 circuit, I have 2. So how many different ways can I break up this circuit?
1,
G, F, 6.
1,
I need somebody to count again.
4.
4. Okay, 4. Okay, so I have 3 ways to remove the first one. I have C to D, C to H, or H to D. I have 4 ways to break up that second one. I can break it up by removing G to D, G to F, F to E, or E to D.
Good.
So I can remove C to D from the first one and any one of these 4 options. I can remove C to H from the first one and any one of these 4 options. I can remove H to D from the first one and again, any one of these 4 options. So how many total do I have? What is my total amount of spanning trees?
12.
What? 12. Simply 3 times 4. I have 3 options in the first circuit. I have 4 options in the second circuit. 3 times 4 is 12.
Is there any other way to make that 3 times 4?
And this one, no. We have one more case.
What?
Okay, so look at this one and look at the graph in your last example. What is the difference? What'd you say, Julian?
They're not spaced.
They're not
like-
Oh,
this one.
Oh.
They're connected by the same line.
Peter, no.
This one. They're connected by H and D.
So, take a look at this picture right here. My circuits are connected by a point. That's okay. Okay? That's okay. They're 2 separate circuits because they're only connected by a point. But when I go to this one,
They're connected by 2 points.
they're connected by an edge.
What?
How are you wearing flip-flops?
Let's go.
It's my northern
That's
blood.
fine.
That's what Mr. Taylor used to tell me all the time. Were y'all here for Mr. Taylor?
No, sir.
It's safe.
Oh,
I was middle school.
So, when you do the redundancy for this one, I still have 8 edges, or I'm sorry, 8 vertices, and I still have 9 edges, which means I still need to remove 2 edges. But watch what happens. I can still remove either C to D, C to H, or H to D on the first one.
Still not gonna be a tree because it's gonna match up to 8.
But when I go to remove from my second one, I have my options of H to G, G to F, F to E, F to D, or H to D. Well, if I rewrite that here again, G to F, F to E, F to D, H to D.
Miss Smith, how did you
H
get
to-
F to D?
That's fine.
I'm sorry, that should be E to D, my bad. You're right, my bad, E to D. I looked at the wrong letter. Thank you for fixing that. Okay, you don't have to, but take a look at this. So, I can remove C to D from this one, and then I have 5 options on this one. I can remove C to H from this one, and then any of the 5 options from the second one. I can remove H to D from this one, but then what happens when I go to remove from my second circuit? Take a look at that last column. What is wrong?
You don't need
It's
to
not HD.
It got HD twice.
I'm removing HD. Well, I sure as heck can't remove it again. So when I remove H to D from the first circuit, I only have 4 options on that second circuit. So now, instead of having 15 options,
14.
I have 14.
So where's the cheat code at?
Cheat code. Where's the cheat code at? So, we started with, we have 3 options in the first circuit, correct? How many options do I have in that second circuit? 5. 3 times 5 minus 1. Is your magic formula. So, anytime you have 2 circuits and they share a line in common, you can't remove that line twice. So, to get rid of that, once you multiply them together, we always subtract 1. Every time. No, we're going to do this. Okay, so let's practice.
You got 8 verses.
Okay, take a look at number 1. So, the first thing I want you to do when they're asking you for the amount of spanning trees is identify how many spanning trees you have, or how many circuits you have. How many circuits are in graph 1? 1. When you have 1 circuit, count your edges in that circuit, you're done. So, I have a circuit here, and it's 4. So that's 4 spanning trees.
Wow.
You're done.
Wow.
Okay. Number 2. How many circuits do I have?
2.
2. Do they share a line?
No.
No. Look at your circuits. Here's circuit 1. Here's circuit 2.
So it's
They
4
don't
times
share a line, so it's 4 times 5.
Yeah, what you mean by sharing a line?
Share a line. That's what we looked at here.
So it,
where the first circuit had an H to D and the second circuit had an H to D.
so you'll do the -1 on the next one.
Yes. So the -1 comes into play in number 3. Because here's my first circuit of 4,
And then 3.
and here's my second circuit of 3.
And then
So they share this line in common right here. So this is 4 times 3 minus 1. So there's 11. Does that make sense?
Yes.
The difference?
Yes.
Okay, so this one is.
So be careful with number 4.
One with -2.
No.
No.
Okay, so we have a circuit here, 4. We have a circuit here, 5. I have a circuit here, 3. I have a circuit here, 3. Okay, so do these share anything in common? No, but this one does. So I need to take care of this first.
That's 8.
So 3 times 3 minus 1 is 8. Once I take care of that, then I multiply by 5 and multiply by 4.
Wait. Why would you?
Jesus Christ.
There is 160 different spanning trees you could draw in this graph. It doesn't. It's hardcore crazy.
One of those should be the chance.
Go off for you?
What?
This is really
Write them all out?
Yeah.
Let me think about it now.
Okay, take a look at this one. This one has 3. This one has 5. This one has 4. And this one has 3. Okay, so this one shares a line in common. So 3 times 5 minus 1, 14.
And then 4 times 3 minus 1.
This one shares a line in common. So 4 times 3 minus 1, 11.
Baby.
Then we have to multiply these two together. And you said 154?
Yes, ma'am.
Can I get it first?
Nope.
They said nope.
Rude.
Okay, I want you to try the next two on your own and we'll go over it.
Man.
Yeah.
And then we've got one more concept to talk about, and guess what? You already know how to do it. Because we already talked about it. Ha-ha.
It's just, I told them on it's about 12 o'clock right now.
Why is you?
Wait, the next two or three? Wait.
Wait, hold up. Yeah. That shares a line, so that is only. Maybe that shares a line, so you have to subtract one. And then this is 5.
You worked hard last night. This one walked in and was like, so can I come back and hang out in the kitchen since you like to get up and sit in my chair at my desk in my space? His boss is just like,
Oh my goodness, Miss Smith, I thought.
Do you not use it?
see, honey. Big blood.
I can't.
I have an answer for it, but I can't.
It's like elementary school.
I have no idea.
No, cause seeing never took me to.
No, it's like some weird.
Second period.
All right. Who wants to go up and do 6?
Is that the 58 bullet done?
Me.
Go ahead, roll. Roll.
Can I do 7?
He wants to do
Get
both.
up,
Oh, he did, oh, okay.
Right.
All big bowling. All big bowling.
If you don't want to trace it, if you just want to put the mathematical stuff
Don't
on
Where's
get
the
it.
goggles at?
Do both of them,
Is
bro.
this the notes you do? What's the answer?
And pull the discrete chapters 5 through 9 and find the chapter 7 notes. It's in there.
Where's the seat? I'm convinced.
Alright.
Going over here.
Wait, hold on. Oh, what? Oh, wait. Okay, then.
Yeah.
Okay, bro.
Yes, track 1.
All right. So number 7. None of your circuits shared an edge in common, so it's simply the 4 edges times the 3 edges times the 6 edges. In number 7, these 2 circuits shared an edge in common. So Raul took 4 times 4, which was 16, and subtracted 1. That's where he got this 15 from. And then times 4 times 5, 300. That's fantastic.
You want some more?
No.
You see it?
I used to be able to bend it to one leg. Oh, yeah, like that. But I'm gonna need to record that so when he leaves, I can just laugh. All right. So this is the last thing. And guess what? You already know how to do it because we did it on day 1.
Oh, well, you're not this strict.
Well, we don't need to go over.
So this should be super easy.
Is he German?
Kruskal? I don't know. I never researched him. So a minimum spanning tree is
Russian?
a spanning tree of a weighted network with the least total weight. So our job is to try to find the smallest spanning tree that is in your picture. Okay, so the problem with this is, take a look at this one. I have 2 circuits. One that has 3 edges and one that has 5 edges. They share one in common. So guess what? I have 14 spanning trees in this picture. Huh? They want me to find all 14 and find the smallest? Say what? Okay. If I move on to network 2, this is 3 times 3 minus 1, which is 8, times 4. There's 32 spanning trees in this picture. Huh? This is getting even worse. If I move over to this one, there is 121 in this picture.
That's a lot.
Huh?
And you want us to
They
find?
want me to do what now?
You sleeping?
Nobody's writing out 121 to find the optimal.
You know, I bet you I know a kid who would do
So,
that.
who?
A kid named Dominic Wesley.
Oh.
He'd do that.
Okay, he's crazy.
Yeah, yeah.
Okay, good to know. So, they came up with something called Kruskal's algorithm. So, remember, we said if there's so many vertices, I need how many edges? One less. So, take a look at network number 1. How many vertices do I have in this picture? 8. So, how many edges do I need? 7. So, I need to create a tree, 7 edges. Did you just come up and steal my notes?
Oh, yeah, sorry. My bad. So to find it.
Can't you just pay attention for like 2 seconds?
Looking at the advanced
We're
one,
trying
I
to
found
do the
that.
advanced, so we're trying to figure out how to get it.
It's not on those notes, is it?
Yeah, it is.
Oh, okay.
Apparently 39. I don't know.
Yeah, that's what I mean. Like, I can't figure it out. And I really should email him and ask him, but I didn't. Okay, so network number 1. I need to try to pick 7 of the smallest edges without creating a circuit. So, what is my smallest edge in this picture? 3. Oh my. Oh. This drives me nuts.
Then you could pause.
Oh, we figured it out.
All right, give me a second and then we'll talk about it.
Wait. Sorry. Gotta continue with those.
Okay, so 3 is my smallest. What's my next smallest? 5. So I have 2 now. What's my next smallest?
6.
There's 3. 7. There's 4.
8.
8. There's 5.
And 9.
There's 6. 10. There's 7. Guess what? That's your MST. That's your minimum spanning tree. The last thing you need to do is add it up. 3 plus 5 plus 7 plus 10, 8, 6, and 9. 48. So, you remember on day 1? Did you figure it out?
Oh, yeah.
Okay, so do you remember on day 1 when we looked at, hold on, when we looked at this one and we picked 4 edges. That's what you just created in this picture, was a minimum spanning tree. Okay, so let's look at the next one. How many edges do I need? Again, I've got 8 vertices, so we need 7 edges. Which edges are we going to use in this picture?
8.
Careful, 8's not your smallest.
7.
7, then 8,
And 9.
then 9. So there's 3.
There's 2 14s.
There's 2 14s. Can we use them both?
Yeah.
Yes. We're not creating a circuit, so we're good. So 1, 2, 3, 4, 5. What's next?
Can't you use 15?
15. I need one more edge.
20. 21.
We have to skip to 19. I can't use 18 because it will close this circuit. So we have to jump to 19. Since you stole my notes, what's the total for this? Oh, I don't even think it's on there because I didn't do this with this. 9 plus 7 is 16, 30, 49, 59, 69, 78,
86.
86? 86. And finally, let's do this last one. So in this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices, which means I need 9 edges.
Start at 4.
We're gonna start at 4.
5.
4 and 5,
8.
8. Wait, why can't we use 11?
I mean, like I said, you can't use 12.
Oh, okay. I thought you said you can't use 11. So 4, 5, 8, 11, there's 4. You said skip 12.
29.
We can use 14. We have to then skip 17.
23.
23,
29.
29,
32.
32,
36.
and 36.
You just don't know what you want to say.
Okay. So it's kind of the same thing as cheapest link. However, I'm not trying to close it off. I'm trying to leave it open, which is easy. It's a lot easier because I can have more than 2 lines coming out of a dot. I can have 7 lines coming out of a dot. It doesn't matter.
Okay, let me get this.
That gives you 162.
You got what?
162.
162?
Yep.
Okay.
I like this a lot.
Questions?
I don't know,
I
but
just like it a
I
lot.
might actually get a good grade on this.
Good. So, here's all the steps that we just did. This is your homework. You've got 3 problems.
Alright.
Oh my.
Okay?
How you sort
Oh,
of
wait,
What was the
this
answer?
Yes.
This is the same. Yeah, this is the same.
What you did yesterday.
Okay. Alicia.